Hi, welcome back to my channel. Today's presentation is about population and sampling. The presentation is a part of a playlist on observational research. I hope you watched previous videos. Now, I need to remind you that today's presentation is a part of a playlist on observational research where we are handling quantitative research methods. And in this context, we are under the observational research family. Well, what's the objective of today's presentation? Actually, the objective is to learn about sampling methods and determine the population sample, representativeness, the population sample distribution, the size of your sample, the probability of sample mean to fall within the population interval. So those are the objective of today's presentation. Now, what will be the content? I'm going to talk about the population and samples, random sampling, sample means and representativeness, the sample size and error, standard deviation, confidence interval, the t-distribution, and some takeaway messages. Let's start with the population and samples. Well, what is a population and what is a sample? Population is a set of all entities sharing the properties under consideration, while a sample is a subset collected or selected from the population for an analysis. Now, why do we use a sample and not a whole of population? We often use samples because it's impossible to analyze the complete population. A well-designed research starts with defining the appropriate population to answer the research question. Therefore, we use the sampling techniques. Now, what is random sampling? Random sampling is very important because first we need to define our target population and we need to define our data sources for our study and for our research and to have a coverage and exclusion, and by that we can define our population. So the population is the aggregation of cases that meets a specified set of criteria. Therefore, we will need always to have eligibility criteria that determines the attributes of our population. Now, when we look at the different sampling methods, there's a lot of different sampling methods, but since we are in the quantitative research methodology under the observational research family, we can mainly focus on the probability sampling. By probability sampling, we mean here random sampling, where we have a sample with a n, small n, drawn from a larger population with a capital N, and we'll have a probability-based approach, and we have representatives. Now, on the other side, when we look at qualitative research samples, for example, we can see the purposive sampling, where we do select respondents through random and snowballing, non-random and snowballing approaches. This could be the opposite for the probability sampling. So again, allow me to reiterate, probability sampling is the essence of statistical quantitative observational research. Now, when we look deeper in random sampling, what are the characteristics of random sampling? First of all, it needs to be indiscriminate, it needs to be unbiased, it needs to be having a large sample. And in this sense, we can go further in detail and use a more sophisticated technique of random sampling, which is called the stratified random sampling, where we can separate the population in smaller groups that are more representatives from a segment point of view, and then we will have the randomness, but it will be distributed among the groups, and we can have these stratified samples, and for sure it's cost effective and it is very relevant and relative. So this is a way to make your random sampling more feasible. Now, what are the advantages of random sampling? Each member of the population has an equal chance of being included in the sample. By that, you can assure that you have a better coverage and a better representation, and every possible sample is equally likely to be selected. Also, even in a random sample, there is a chance that the sample population is unrepresentative, but in the same time, we try to prevent that. How do we do that? To prevent this, we increase the sample size, so the larger the sample, the lower the chance of getting lopsided samples. So this is simply the advantage of random sampling. Now let's talk about another important topic, which is the sample means and their representation. Now, when we talk about sample means, one of the most important calculations we need to conduct is calculating the sample means. And always we will have two means. One mean for the population and one mean for the sample that we collected or the data we collected for our sample. So the population mean should be calculated to estimate the sample representation, and by that, as you can see in the formula, we will have simply the mu, which is the population mean, which is a sum of all items that we measured divided by the number of items in capital N, and by that the N will be the number of items in the population. By that we can have the population mean, and then we will need to do the same exercise with our sample mean, and from there we will have the sum of all items in the sample, which is the x, divided by the small n, which is the number of our item sample, which is the smaller one. And by that we can get the x bar, which representing the sample mean, where the small n is the number of items in the sample. So this is the calculation method that we use in order to calculate the means of the population and of our sample. Now it's very important to distinguish the x bar and the mu to estimate our sample representation. So actually the difference between the sample mean, which is the x bar, and the population mean, which is the mu, is called the sampling error. The larger the sampling error, the more I have a difference between both of them. The smaller the sampling error, the better I have a representation. So it's very important to work on this sample mean. And in this sense, we try to ask ourselves, how seriously can we take this sampling error and how far can we reduce it? But let me now move to the next important item of today's presentation, which is the sampling error and the influence of the sampling error on the size. In fact, in order to reduce the sampling error, we must increase our sample size. The larger our sample size, the smaller our sample error, and by that we achieve higher representation. Now, when we look at better representation, we need to look at the difference between the sample mean, which is the x bar, and the population mean, mu, which is called the sampling error. By that, we can have a negative or a positive value, and the more we draw random samples, the more we reduce the sampling error. So actually we are increasing our sampling and we are increasing our sample size, we are repeating our sampling approach. By that we are decreasing the sample error and we are increasing the sample size. Now, the sample size is a very important aspect, and many people are confused about how to define a sample size, what is the appropriate sample size when they are starting to do a sampling. There's many methods. I will explain to you at least two methods in this presentation. So the first option that we have is that we work with the minimum sample size. And this is simply that, depending on your field, you will find some recommendation in your field for what is a recommended sample size. It can vary between 30 subject up to 3,000 subject, and sometimes it can be also defined as a percentage, something like 2.5 of the population. So this is one of the ways to define your sample. When I say field independent, I mean that you go back in the literature and you go back to the experts in your field and you ask them, what is the minimum sample size in my field of domain, depending on your study field and depending on the topic you are working on, because sometimes if the topic is still not explored, not a lot of research has been done before in this area, we can tolerate small sample sizes, but then the expert has to tell you that, or the literature. How can I do it in literature? Can see what has been published in the last 5 years, any study that did observational research, and I see what was the average sample size, and I take a similar average or even a little bit higher value for the sample size, and by that I distill or I extract this value from expert or from literature. Or like I say here, the value of 2.5. Also, there is another way that we can use, still as option 1, is to have a minimum sample size that can be estimated using a specific software, which is called G-star power software, for the difference between two dependent groups, assuming that the main statistical analysis would be a two-tailed logistic regression and effective size P of 0.05 and a statistical power of 0.8. So under these conditions, I can use this software and I start to put these basic hypotheses for my sampling, and I can use this software, which is a tool to compare or compute statistical power analysis for many different t-test, f-test, x-square test, z-test, and some exact test. I leave for you the link here if you are interested. Also, this could be a way to explore another way to define your sample size. Now let's move to option 2, which is a totally different approach of defining your sample size, because it depends mainly on your survey. It depends on your questionnaire that you are going to develop and the number of questions that you will have. In fact, calculating your sample size under option 2 is based on a rule of thumb that is used in factor analysis. And what do we do there? Actually, you will be required to have at least 5 times as many respondents should be as the number of the items or the questions of the questionnaire to estimate the sample size. And I advise you strongly here to watch the video on questionnaires design or survey design. It's a previous video, because from there you will learn how to define your items or your questions in a questionnaire, and based on this rule of thumb here, you will have 5 times the number of questions that you have in your survey. And this has also a method that has a well-established reasoning and logic behind it, and I leave for you the references if you are interested to build on that. But now let's move to a very important theorem that we all use in order to justify the sample size and make sure that our error of sampling is small. Actually, since we are falling under the probability theory in order to conduct our random sampling, the sampling distribution of a sample means approaches a normal distribution as the sample size gets larger according to the central limit theorem. Well, the central limit theorem, what does it say? The data should be sampled randomly, the sample should be independent of each other, and the sample size should be sufficiently large but not exceeding 10% of the population. So as you can see, I mentioned earlier 2.5, here it's 10%. For sure in many situations it's very difficult even to reach the 1%. So it's very important to understand the central limit theory, check the 2 options I mentioned about the sizing, but meet those 3 criteria that the data should be random, the sample should be independent of each other, and the size should be large enough but not exceeding 10%. Also, when we are assuming in our central limit theory that the normal distribution of your sampling, we must think that the sampling distribution of the sample is a normal distribution. As the sample size gets larger, and according to the central limit theorem, we discovered that the more we draw a sample, the more the distribution will look like a bell-shaped normal distribution, as you can see, and from there we can improve our representation and reduce the error of our sampling. Also, it's very important to look at the size of our sample and the frequency so that we make sure that under the condition or the central theorem of normal distribution, we have a higher representation with a low error and a large sample size. Now allow me to move to another point which is very important, which is the standard deviation and its importance. But allow me to explain first what is standard deviation. Well, under the normal distribution conditions, the standard deviation measures the spread of the data, which is simply equation in a mathematical approach. We do a square root of the variance. As you can see in the equation, the sample mean has a standard deviation that can be calculated. We will have sigma, which is representing the population standard deviation. We have a capital N, which is the size of the population. We have a xi, which represents each value from the population that you worked on, and then we will have a mu representing the population mean. Based on the sum of the x minus the mu squared under the size of the population, all that root squared, we can get the sigma, which is the population standard deviation. Now, this is very important because based on that, we can start to better understand the distribution of the sample, and we can better also understand the distribution of our population. Now, what's the problem that happens in many situations? That we don't know the population standard deviation because we do not have statistics or data that represents the whole population. So in this case, if it is unknown and if we don't know the sigma, which is the population standard deviation, we refer to the t-test. And the t-test is a t-distribution test that allows us to calculate the population standard deviation. Now, the standard deviation of the sample mean declines as the sample size is increasing. So actually, the more I have a larger sample size, the more I have a lower standard deviation. And if I have a very small sample size, I will have a very high sample standard deviation value, which is bad. So as you can see, the higher the standard deviation, it's bad. The lower the standard deviation is better. Also, what we can do, we can start to segment our standard deviation. So what we do here, we do normal distribution data, and it is used for prediction because this allows us to predict, and we start to have a rule of thumb that says all data fall within 3 standard deviation from the mean. So we have 3 categories that we use. One is the 99.7 percentile, the 95%, and the 68%. And we try always to make sure if our sample falls in which of those ranges. Now, as you can see, we try to estimate how far your random sample is distant from the true population mean. So here what we do, we calculate the probability that is a normally distributed sample mean will be within. And here we have the 3 aspects like I showed you in the visualization, the 3 categories. Either we have a 1 standard deviation of its mean under the 68%, or the 2 standard deviation of its mean by 95%, or the higher quality will be the 3 standard deviations of its mean is in the range of 99.7%. In other words, this means that a random sample mean has a probability that under the normal distributed sample mean will be within 30% to 32% chance of being more than 1 standard deviation away from its mean, or having 5% chance of being more than 2 standard deviations away from its means, or 0.3% chance of being more than 3 standard deviations away from its means. So the lower we go, the better it is, and this means our sample is representative, it's large enough, and the range of error is small as possible. Now, in summary, what we can say about standard deviation, well, the sample mean has a sampling distribution that should be approximately normal, and the more samples are drawn, the closer our sample mean that we collected ourselves equals the population mean, and that's what we want to make sure to assure the representation. So the standard deviation measures the spread of the data, and sigma is the standard deviation of the population x divided by the square root of the sample size small n. Now let's move to another important parameter that we calculate, which is the confidence interval, or another test which is very important, which is the confidence interval. And the confidence interval definition is that it is a range where the true mean can be found with certain probability. So by that we can calculate how confident we are that our mean of our sample falls within a certain range. As you can see, if I have a large population there on the left side, and I will collect my own samples, sample 1, sample 2, sample 3, every time I will calculate the mean of my samples and I will try to compare it to the mean of the larger population. And based on that, I can define, from this difference, I can define the confidence interval. So each sampling here from those 3 samples is likely to come out with a different mean. And now it's very useful to define this range between all those 3 different means in which the true value will lie with a high probability. Based on that, or by defining that range, I can call it the confidence interval. The smaller it is, then I have a high confidence interval. The larger it is, I have a low confidence interval. So it's very important to calculate the confidence interval to estimate those differences and this range of the different means of the different samples that I collected. Now, in order to calculate the confidence interval, we rely on a formula which is a probability base where we try to find the true mean with a certain probability. And here we look at the confidence interval, which equals the sample mean plus minus z, which is the confidence level value, and this is multiplied by s, which is the sample standard deviation, divided by the root of my small sample size. Based on that equation, I can estimate my confidence interval. Now, after doing that, I can start to estimate the probability, and like we mentioned before, it could be a 95% or a 99% probability, which is used often, where the sample means lie within the interval, and based on that, I can proceed with my calculation. Now, allow me to move to the t-distribution, which I mentioned earlier. Especially we use it when we do not know what is the sample, the population mean, and here, therefore, we have to use the t-distribution. And as you can see, when we are confused about the sigma, and we don't know what is the population variance or the standard deviation of our population. In this case, we don't know how to calculate the sigma. What should we do? Actually, we go directly to the option no, where we are forced to calculate the t-distribution test. What is a t-distribution test? It's a quality assurance test, and it will allow us to calculate the unknown sigma, and it will be replaced by a sample standard deviation S. So here, if we replace it by S, it is called t-statistic or t-distribution or t-score, and the t-statistic or the t-distribution is always used if the size of my sample is very small or I have an unknown sigma value. So this is very important. Now I'm done with the presentation of today. Some takeaway messages before leaving you. Well, we talked today about population and sampling, and we presented a lot of tests. But first of all, a sufficiently large sample that was drawn based on a random sampling of your population of interest will have similar properties as the parent population. So the more you make sure that your sample is very close and similar to the larger population, the better that you can use it in your statistics and in your relations, correlation test, regression test, analysis in general, because it is as much as possible representative. It has a small range of error, it has a large sample size, and it represents the population in a random way. Another important key message or takeaway is that the properties, however, will not be exactly the same. Due to the central limit theorem, you know that your sample mean is normally distributed. So this is also an important message to take into account. Also, you can therefore be sure that any sample drawn will be within 95% confidence within 2 standard deviations from the population mean of 1.96. And finally, by calculating the confidence interval using the t-distribution, you can calculate the low and upper boundary of the true population, and you better characterize your sample and your population. Well, that's it of today's presentation. I invite you to watch following videos on observation and research. Today's presentation was about population and sampling. I hope you learn from it and you apply it in your research. Thank you very much for your attention.